Welcome friends. Today's session we will continue our lecture series on solving previous year GATE questions. Question which is appearing on your screen is the question from EDC subjects first module, that is semiconductor physics. This question appeared in the year 2021 for 1 marks. This is the one out of the two questions appeared in the same year. Now let us start solving the question. So let us first understand what exactly is given in the question and what is expected from us to obtain from the given data. So now what it is saying is, this is a semiconductor bar which is doped p-type, where the Fermi level is constant, the size of the bar is L, capital L, and we can say this is under equilibrium condition. Means it is in a steady state condition, nothing is changing right now, it has reached the steady state. So now you can see here Fermi level here is constant and valence band is moving, means it is changing. Why it is changing? It is given further that the doping of the p-type semiconductor is not uniform, it is a non-uniform doping along the length of the bar. Now we can say that because of that, the distance between the top of valence band, that we call it as EV, and the Fermi level EF will not remain constant. As the doping will increase, Fermi level tends to move more closer as comparatively to the valence band, or we can say top of valence band comes more closer comparatively with Fermi level. So let us discuss this in more detail. First we will see exactly what we need to find. So further it says this movement or this non-parity or non-constant difference between the Fermi level and top of valence band is delta. Means here at z equal to 0, the change in a Fermi level or whatever the distance between the Fermi level and EV will reduced by the amount delta at z equal to capital L. Now what he wants us to calculate is, based on this criteria, what is the built-in electric field which is generated. So let us first start with the concept of Fermi level, how it moves, and then we will move forward. So here you can see in this figure, in this diagram, that for an intrinsic semiconductor, the Fermi level lies in the middle of conduction band and valence band. Means at the bottom of conduction band and the top of valence band, the forbidden energy gap, the Fermi level lies at the middle of that. And as soon as you dope this intrinsic semiconductor with p-type or n-type impurities, it will move eventually. For n-type, it will move closer to conduction band, as you can see here in the second part of the figure, here in n-type. And for a p-type semiconductor, which we are considering right now, it moves towards the valence band, near to the valence band, that is downwards. So now this movement depends on how much doping you are doing. The more the doping, more the Fermi level comes closer. So now we can see from this second diagram on the screen that here we are considering the Fermi level as constant, as it is a mathematical tool. Fermi level, as you know, is a mathematical tool. So we will consider it as constant, and then we are calculating the top of valence band based on the relation or the difference between the Fermi level and top of valence band. So our top of valence band is rising, or the difference between Fermi level and top of valence band, that is EV, is decreasing. I can see at z equals to 0, you have zero displacement of Fermi energy level from intrinsic level. So we can say the change, here we can write down the change in EV with respect to this for z equal to 0 is 0, means it is at place. Now it is moving and linearly it is changing. So when you reach at z equal to L position, we can say that the change in EV for z equal to L is delta. Now what we can say here is the change in EV, the total change in EV from z equals to 0 to z equals to capital L will be DEV is equals to DEV for z equal to L minus DEV for z equal to 0. So this is not dx here, which is here this will result into delta minus 0, that is your delta. So in this figure we can say change in DEV is equals to delta. And what is the change in x? From change in x or z in this case. So we should write down x here. So what is change in x? Change in x is dx, which is equals to L minus 0, which is equals to L. So this is the change in x. So now what is an electric field? Electric field is due to, or built-in electric field is due to non-uniform doping. How? As the doping is changing, the diffusion will take place and a built-in electric field will get created. So the change in top valence band level, that is energy, with respect to the length will be your electric field, as you can see here in the next slide. So this is the formula for the electric field, which is 1 over q, means q is the how much charge you have, that is generally for electron is constant, and change in top of valence band with respect to change in the length. So what is top of valence band? It is your delta. So it will be 1 over q delta over capital L, that is your delta over q into L. So now once we move back, we can check the 4 options and we can say D is the correct answer. Thank you.